Hello, welcome back. So today we are going to close out our week 3 set of lectures, right? So the back half of this, and I think we're going to be just a little bit short. We're going to rehash some of these details anyways in the next week's material. So we don't necessarily need to get to all of it today, but let's see how far we can get. Last time we left off talking about different methods of heat transfer. Right, so we said that there are 3 big ways that we normally consider how heat is being transferred. That is either by conduction, when 2 objects are pressing up against each other. That is by convection, when a hot fluid is moving somewhere that's a little bit more cold. For example, like your computer fans running right now. The third is radiation, and this is one that is happening constantly, no matter what. Can't stop it, always going to be happening no matter what. Anything that has temperature is constantly emitting all of this different light all over the place, and everything with temperature is everything in the universe. There's nothing that doesn't have temperature, so everything is constantly doing this kind of heat transfer. That's why everything, no matter where you're at, can eventually feel some heat from something, somewhere or another. But let's go ahead and dig into this just a little bit more in a little bit more detail. I want to start with conduction again. Normally what's happening here, right, a hot temperature object is generally going to have a lot more buzzing going on in the atoms. So all of those atoms are sitting in place, they're buzzing very frequently back and forth. When they get put in contact with something that is not buzzing as quickly, those fast buzzing atoms are kind of knocking into, shouldering up against those colder atoms, causing them to buzz a little bit more, and then likewise to their neighbors until we see that heat transfer all the way through. Right, that's a lot of the time why you can feel a little bit of a heat difference in a pan, especially a big pan like a wok is fantastic for this. On a stovetop, right around the upper lip of that wok, you're not going to feel nearly the same kind of temperature as you do right at the bottom of the pan because, well, it's got to start from that hot source and then slowly spread to the outside. So eventually the whole thing will get hot, but especially right at the beginning, you can still pretty safely touch that outside, even if the bottom of the pan is starting to get very warm. Important examples of this otherwise, right, this is an energy transfer from the surface of the Earth into the atmosphere, and then convection actually takes over. Energy transfer through walls, windows, roofs, right? If you touch something cold outside, that's conduction. Of course, anything we put on the stove, that's conduction. There's a lot of different examples of this. It's also a pretty easy one to talk about. Like numerically, we can come up with an equation that does this pretty well. And it looks something like this. This is the equation that we use in physics, at least. The belief is we've got one side that's hot temperature, we've got one side that's cold temperature. There is some sort of medium separating the two of these things together. And that medium that we're looking at here, it's going to have some sort of thickness, it's going to have some sort of surface area, and heat is always, always, always going to flow from a hot temperature place to a cold temperature place. So breaking apart these different variables here, we've got that surface area, right? The more surface area, the more heat transfer we can accomplish. We've got that distance between the two. So that is to say, if I put more and more material between my hot and my cold, then it's just going to take longer for that heat to actually transfer through. I've got the temperature difference, of course, is a very important feature here. Looking at that temperature difference, the greater the temperature difference, the more rapid the heat exchange. Right? I think that makes sense. Touching that, slightly warm pan versus touching that very hot pan, right? Even if we touch it for the exact same amount of time, the rate of heat transfer is much greater from the hot pan, mostly because it's got a lot higher temperature. Your hand's the same temperature, you touched it for the same amount of time, but because it's much, much hotter, it's able to transfer heat a lot more quickly. And then finally, of course, this value that I kind of skipped over at the beginning, this value K, what we call thermal conductivity. What this is it's unique to every material. So the higher K is, the better a conductor that material is. So comparing some of the numbers here, we can generally see, we don't see a lot of them here, but we do see aluminum, we do see steel. Some of these metals generally are very good thermal conductors. Silver, copper, fantastic thermal conductors. They've got a very high thermal conductivity. But then you can compare that to something like what's going on in other insulation, like styrofoam or urethane foam. Both of these have a very low thermal conductivity, which is a feature, right, of materials like that. You don't want to be conducting heat. You want to generally be trying to trap heat somewhere. So the idea that they have a very low thermal conductivity is to their benefit. So you might notice here on the right column, this nonsense, right? If you're at all familiar with our units, we're looking at the left-hand column here. We've got watts, meters, Kelvin. Those are all standard units. Those are all units that I've talked about that I personally like because, you know, that's what we use in physics. On the other side of things, we've got BTU, inches, hours, feet squared, Fahrenheit. Yikes. This one's kind of a mess, if I'm being completely honest. There's, you know, some strange things going on here. But this is what happens when we start to think about standard units. And I bring this up, we include this in the table, not because thermal conductivity in these units is a common thing per se, but it gets used in a quantity that's a little bit more common, especially as a consumer. Right, looking as a consumer, if you were to go out shopping, you wanted to be looking at something like insulation for your home. I know we're talking about riveting stuff, but realistically, right, this is a decision that you're probably going to have to come to at some point in your life. So you're looking at different types of insulation. Most of the time, insulating companies don't market their values based on the thermal conductivity in standard units. It's just not feasible. Right? It doesn't mean anything to the average consumer unless you've taken a physics class, unless you've heard material like this before. A number like this is mostly meaningless. So instead, what they use is an R value. And the R value is just telling you roughly in a manner of comparison, how good of an insulator are you looking at? And there's a little bit more consumer friendly because for one, the equation's a little bit simpler. Right, we're looking at an area, a temperature difference divided by R. So the bigger R is, the lower your rate of heat transfer is going to be. But the other benefit of having something like an R value is that when we're talking about R values, it's very easy to stack up and get a total amount of insulation. Talk about it in just a second here. For now, let's look at some common R values, see where some of these things would actually be. So a comparison of a lot of these different things. Notice here that we're talking about air layers as well, right? Because technically speaking, there's, you know, a little bit of insulation from that air just as well. But most of what we're looking at insulation-wise, you're going to notice in a column like right here and a spot right here, some of these different spots are common insulators used. If you're looking at like 1-inch foam, for example, that's something that gets commonly used in tight spaces. Windows have a lot of variety here. Because realistically, if we go back just a little bit, looking at something like glass, glass doesn't have the tiniest thermal conductivity of these, but it's pretty small, all things considered. So glass doesn't have the tiniest value here, which kind of generally means that it's not very good at insulating your home. You'll know this especially if you've ever lived in or visited any sort of older home that doesn't have very nice windows, right? A lot of the time that's a single pane window. Oftentimes you'll know because it's a little bit noisier, right? You can hear sound pretty well through that window, but it is noticeably colder during the wintertime near that window because, well, a single piece of glass doesn't do a lot to insulate. So when we start to go down a little bit more, looking at some of these window values, what we start to get at though is we've got like an argon-filled double glazed with E coating, argon-filled triple glazed with E coating, best commercially available. What's happening here is that we are talking in part about what's going on with the window frame, because that is important as well. But the bigger part of this is you might have heard of things like double-paned glass. So what they're doing with something like that is you've got one layer of glass, you've got a layer that sometimes, again, has something like argon inside of it, sometimes it's trying to be vacuum sealed, but generally, we're trying to do something with that middle layer, something that is very not thermally conductive, like glass regularly is. And by kind of trapping that layer in between two other slides of glass, what we get is a much higher R value, a much lower net thermal conductivity out of the same window. But of course, doing something like that, it's a little bit more expensive. So I want to talk about one problem here, and I know it's a little bit busy with what we've got going on here. So let's take a look at what we've got going on. let's imagine we've just bought some sort of old house, so it has very little insulation, or if any at this point. It is 36 feet wide, it is 24 feet deep, it is 17 feet tall, which is honestly really tall, but that's all right. Right, we've got kind of a boxy house here, is what we're really looking at. The walls have no insulation. The R value of the wall materials by themselves, and then the dead air kind of next to them, is only 4. Again, compare that to some of these other values that we're seeing here. Very low insulation from just the walls by themselves. Generally, ceilings are a little bit better, right? What we're seeing here is we've got an R value of the ceiling 13.3, because generally heat rises. Right, so if you're talking about heating the home, that's where a lot of your energy is going. You're worried about losing that heat, and heat's going to be rising. You generally want to put your best insulation at the top. So this is not this is not an unusual thing to see 13.3 for only the ceiling value, and then the walls are just kind of left to their own devices. But let's go ahead and say completely, it's a full-on box other than that. Let's go ahead and imagine it's a cold day outside, only 10 degrees Fahrenheit. 68 degrees Fahrenheit inside, because again, you don't have a lot of insulation. You're trying to keep that power cost down. What is the rate of heat loss through the walls and ceiling? All in all, up in total. Now, let's imagine you're also trying to keep this house heated, trying to maintain this temperature using something like an oil stove or an oil furnace or something like that. Or even just a space heater. A kerosene space heater does pretty well. So, when we're comparing it like this, considering some of these values here, one thing that I do want to highlight is, how do we know how much oil we need to burn? Well, we need it to be so that the energy gained from burning the oil is exactly matching the energy that we're losing due to the just heat dissipation into the cold winter. Finally, if we're looking at $2.75 per gallon of oil, which I know that's fluctuated quite a bit here, but that's a not unreasonable value, how much would it cost to heat this house for a month? So, like usual, I'm expecting here that you're pausing the video somewhere around here, giving yourself the chance to at least work on this problem, get at least through the setup. If you need a little bit of a hint, you can come back and start to watch, but I really do recommend try this out yourself. Okay, so I'm assuming that you are coming back, having done this problem. Let's talk our way through this one. And this one actually, I've got a worked out solution. It's a little bit dense here. So I think what we might do is we might try to split this apart in a couple different pieces, right? Let's focus on just part A for now. Let's kind of separate this thing out. And we can talk about the different spacings that we're seeing in a spot like this. So, first thing that we've got, right, we're looking at the different walls. Because if we're talking about what's going on with that heat transfer, we need the total surface area that heat is going to be moving through. We need the difference in temperature between those two spots. And finally, we need the R value of that particular area. Since we have two different R values, what I'm going to do is I'm going to find two different areas, right? We're going to first find the area of all the individual walls because they have that R value of 4, and then we're going to find the area of the ceiling with its other R value, and we'll combine those answers together at the very end. So looking at it like this, hopefully that starts to become a little bit more clear. So our first section right up here is talking about taking just those walls. We've got two walls that are 36 by 17. We've got two walls that are 24 by 17. Combine those together for a total of 2,040 square feet. And again, I know our standard unit is always going to be meters when we're talking about distances, so we typically see this in square meters. But again, R values are a more consumer-friendly thing. Because this course is based in America, R values are going to be based on those American units, or the imperial units. So we're seeing things like feet, we're seeing things like BTU, we're seeing things like hours, not quite standard units. But not to worry, all of these R values, if you're plugging in with those standard units, and we can even check the values here, right? Feet squared, Fahrenheit, hours, BTU, all those things combined together. And there's even here at the very bottom, if you notice this, there's a way to convert that to SI units. So you can transfer back and forth between the two. But I'm just going to go with the units that we've got here on the table already. So with that, we've got our square footage of the walls. we're going to do the exact same thing with the ceiling here. And for all of these spaces, we've got a delta T of 58 degrees Fahrenheit. So separating these things out, let's go ahead and separate that out just a little bit more. So for the walls, the heat rate transfer is 2040 times that 58 divided by the R value of 4. The units are a little bit crazy here. We do the exact same thing for the ceiling, much smaller area, but it is only one single square rather than the 4 that we're seeing for the walls. Combine those values together, we get a total of 33,348 BTU per hour. So a pretty consistent amount, right? That's not an insignificant amount. BTUs are not tiny units necessarily. But how does that compare to oil? So what we can do here is we can say, all right, well, let's take 1 full month, right? That's the premise of this problem. In 1 full month, how much are we going to have to burn? I'm going to say, based on some of the values that we've got from some of these other sections, we've got about 138 kilobtu per gallon, right? So 138,000 BTU per gallon. We've got this total amount of energy that we need, 2.4 10 to the 7th. Since we're only 80% efficient, that means we're not actually getting the full efficiency of any heat that we're putting in here. The way that we can do this, any efficiency equation is always looking at the efficiency is equal to what we get out versus what we put in. So in this case, if we're looking for how much we have to put in, we know how much we're getting out, or how much we want out, I guess. We know what the efficiency is. What we really want to know is how much oil are we going to have to burn? Solve this out. So the amount of energy we're going to have to burn in total is work out, or the heat out, divided by the efficiency. 80% efficient, so it's not a huge difference, but it bumps all the way up to 3 times 10 to the 7th. And then when we use that value of oil per gallon, we get a total of 217 gallons. Not an insignificant amount at this point, right? But there aren't a lot of oil furnaces, arguably, right? Most of them are natural gas at this point, but that is still a pretty considerable amount. If we're comparing this just directly with gasoline, for example, that's about $600. Now, furnaces probably aren't actually going to use gasoline. They're more likely to use something like kerosene, but, you know, this is a good price point, I think. It's an easy comparison. There's going to be a little bit of a difference, but around there, around $600. So why might we do a calculation like this? Well, realistically, anytime you're looking at something like insulation, at the end of the day, the hope here is that any money you're investing, you're going to get a return on that investment. Looking at it like that, right? Insulation is always better to have. It's always going to be a good thing to have better insulation. You're always going to save a little bit more money by having better insulation. But the question is there a certain price point that buying the next level up of insulation just doesn't make sense financially? Say you want to have earned your money back from the insulation in 5 years. What you can do is you can compare some of these different values. You compare an insulation value with that R value of the insulation you're looking at. You compare that to what's going on if you had instead bumped up to that next level. Look at the difference in the cost here, right? And that's coming from a cost like this, cost from heating. You're going to need to get that heat no matter what. It's just how much of it are you going to need. So look at the difference between those costs. Now the question is, okay, well that's the difference between the cost. How much do the insulations actually differ in cost? If I'm going to be getting this much of a difference per month by upgrading, how many months is it going to take before I'm earning that money back in full? And then I can actually start saving money in the long run, right? Short-term investment, or not, I guess not it's a short-term upfront cost for a long-term benefit. And then you've also got to contend with, well, when are you going to next do an upgrade, right? That's usually kind of the upper limit. If you're not going to make your money back by the time you get an upgrade again, it's probably not worth it to go for that higher grade. Probably better to just go with the stuff that's a little bit more affordable. Now, normally, you might have to deal with an inspector to do this, and admittedly, right, this is a little bit of a simplified calculation. There are a lot of pieces missing here, right? Furniture has an impact, windows have an impact, the different beams in the walls have an impact. All of those things do have an impact. But this is what we would call like a back of the envelope kind of calculation. It's a little bit short, it's got some numbers in it, but it's a calculation that at the end of the day we could ultimately do, and instead of paying out a couple $100 for an inspector to come around, we can calculate these numbers ourselves, right? Help improve on our return of investment just a little bit more. So, moving right along here, right? Another reason that we like these R values is because not only are they a little bit easier to calculate, but it actually turns out that whenever you're dealing with multiple different layers, so in this case we've got dead air, we've got the drywall, we've got the fiberglass, we've got the outside wooding, and then we've got another layer of dead air on the outside. All of these things combine together as a complete insulation layer, right? No single one of these is necessarily completely isolated. The R values are very nice because what you can do is you can just take the R values of every individual piece and add them all up together, and that's your total R value for that particular area. Very nice. That is not something that we can do with the physics equation, right? This one really only counts for one single material being there. If there are multiple materials, this gets a lot more complicated very quickly. So that's really the reason why the R values are a lot more consumer friendly. And also why you see R values without any sort of mention of thickness. That's another key spot, right? When we're mentioning these things, look at what we've got going on. If we're talking about 1/2 inch cedar, 3/4 inch oak, these things are already telling us about the width. There's no width mention in this equation right here. Really what we're looking at is just for a given width, it's got this R value. The width of the material is already predetermined. So, a little bit easier, but a little bit less flexible. It doesn't apply to necessarily every single material. So, convection, right? This is the bulk movement. I've got a hot fluid somewhere, be that air or water or some other, any type of fluid, air or liquid. It's got some heat. I move it to a place that's a little bit more cold. It transfers that heat. In place of that hot fluid, I pump in some more cold fluid to suck up more heat, send it out the other way. Fans do this fantastic, right? You might notice when you start running your computer a little bit harder, those fans kick up just a little bit, right? That is your computer noticing that there's more heat inside that it needs to get rid of. It's very difficult to just kind of conduct that onto other things. So instead what it does, it brings in cool air from the outside, it heats it up with a heat pipe and a fan, and then it spits it back out to the outside where it can transfer to the rest of the room. If you've ever had a really big computer, I've got like my desktop next to me, and when I leave the door closed and leave this ring running for a while, I'll start to notice the room is noticeably a couple degrees warmer than the rest of the downstairs area that I'm in, largely because, well, it's pumping that heat out. So conduction is still very involved in convection, but generally speaking, this is a good way to get a lot of heat moving very quickly. When you're actually looking at something like water on a stovetop, it's a little bit different because this process actually happens naturally. A warmer fluid generally is less dense. Things that are generally less dense will float to the top, right? So that hotter fluid becomes a little bit less dense, floats to the top of your pot, releases that heat into the air as steam, cools down a little bit, sinks back down to the bottom for the process to continue, and we get these cycles in and out. Now, that is a process that is pretty natural with a lot of other things. Let me go skip ahead to this really fast. We call that natural convection because it's just what happens in gravity, right? If we're on a planet, so this doesn't work in your future space station, not as well at least, but when we're on Earth where we've got that effective gravity, natural convection does just that. Those less dense things rise, give away their heat somewhere else. If we want to do this ourselves, like they do on the International Space Station, then we'll use fans or pumps or something else like that. We just call that forced convection, right? We need that convection to happen. It's not happening naturally, so we're going to make it happen. Or in the case of some computers, right, even my desktop right here, heat would naturally flow out of the top of this thing, but it's a little bit slow. The fans move that air a lot quicker, so that's what we use. Forced convection can be a little bit more forceful, but it does take a little bit more effort to do. Now, some other places where natural convection happens, right? This is actually happening all around the world. And admittedly, this is a very simple picture of what's actually going on, right? Realistically, there are all sorts of air and ocean currents traveling all over the world in different paths. So to draw it like this is a little bit of a simplified view, but it happens on both small and very large scales. So finally, the last one here, and another one that we've got a little bit of a crazy equation for, is radiation. So let me go ahead and skip ahead before I talk about this just a little bit. All objects are constantly emitting light. It emits light in actually what we call a blackbody distribution, or the Stefan-Boltzmann distribution, which is a fancy name to basically say that there's this really big curve that has infinite ends, and it's telling us exactly what the distribution looks like of radio waves, microwaves, infrared, visible light, all the different colors of light. Now, in this picture, we've broken them up into three big categories. We've got everything going on in the infrared, that's your microwaves, your radio waves, and then, of course, infrared. We've got the visible spectrum, the stuff that we can see, and then we've got the ultraviolet, which is UV, gamma, X-ray, stuff like that. So, generally, right, if we're looking at like Earth's temperature, we're a little bit warmer than Earth, at least on this scale. So we're right around in this region where very nearly 100% of the light we emit is infrared, right? That's why you can have a glowing personality, but generally not a glowing body. Doesn't quite happen like that. Our eyes aren't sensitive to that light. But if we do start to ramp up that temperature just a little bit more, I talked about this last time, about a burner that's been turned on high, right? You'll start to see that visible glow. That's not to say that it's now primarily visible. All that's saying is that there's a ton of infrared, and there's a little bit of visible, but by how much light is being output at that point, it's enough visible that we do start to see it, and at some meaningful level. So by the time you're getting to something like an incandescent lamp, right, those incandescent light bulbs that I keep talking about, those things get extremely hot. Very, very, very hot. They're a very tiny wire with a lot of current going through them. So it's, a pretty impressive engineering feat that they're able to maintain that temperature for so long. But you can see that a very significant portion of that light is actually coming out as infrared, right? Not all of it. Of course, we do get a fair amount of visible light, but a lot of it is coming out as infrared. And that's actually why light bulbs are so inefficient, because so much of the light is coming out as infrared, and so little out of it is coming out for visible, and visible is really what we're trying to use it for. Right? Of course, if you're in a downstairs kind of half basement like I am, incandescent light bulbs are kind of nice because they provide just that little extra bit of heating for an otherwise really cold space. But for most other uses, incandescence, most of that energy is just going into places we don't care about. So that's why LEDs and some of the other, precursors to that, like the rare gas lights, that's why they were so appealing at the time. They didn't require nearly as much energy because less of it was going into useless places. By the time you get up to the sun, we can see about 40% infrared, 40% visible, 20% ultraviolet. That ultraviolet is actually pretty dangerous. That's what's responsible for giving you that sunburn. But if you remember, going back a little bit here, that ozone layer and the aurora borealis, a few of those other features of Earth help to block a lot of that UV radiation in the top layers of the atmosphere so that by the time it gets to us, it's really not too bad. Right, still is some coming through. That's why we do need to wear sunscreen most of the time, but not nearly as bad as if we were just exposed to it directly. So let me back up. With that in mind, this equation right here is telling us about the full power emitted. And power here, being very careful, not the energy, it's the power, it's the rate of energy. So we've got a couple different variables. We have this emissivity constant, which is just somewhere between 0 and 1. For the most part, we're always just going to say it's 1. Unless specified otherwise, it's just 1. What it is some materials are not so good about giving off particular colors of light. And generally for those things that are not so good at giving off some of those colors, it takes a knock to that value. It dips a little bit below 1. But for us, let's just go ahead and say it's 1. It makes everything a little bit easier, but I felt like I should include it just in case. 5.67 times 10 to the negative 8th. This is one of my absolute favorite constants in physics. And yes, I am one of those people that keeps a favorite, largely because it's simple. It's 5, 6, 7, 8. I love it, right? I also play a fair amount of music, so that just vibes with me on a couple different levels there. But this is known as the Stefan Boltzmann constant. If you want to read a whole lot about it, I've got all sorts of things down here. There are certain things that get me rolling sometimes. So if you want to see something, it's got a little bit of a story down there. Third, we've got surface area. Right, and that is the outside surface area of whatever that is, right? Where I'm emitting from right now, where it's actually escaping is all of my hands, my face, my head, places like that, right? Any of my internal bits, all of those will be radiating, but it's just going back into my body. So it's not really going out in that sense, right? That surface area is the external area facing away, getting all that radiation away from me. And finally, the last thing that we've got is temperature. And I've got this highlighted in Kelvin because that is very important here. And this is kind of unique. It is T to the 4th power, which we don't see in physics very often. But kind of a cool value on that one. We absolutely need to be in Kelvin. We cannot be in Celsius. We cannot be in Fahrenheit. Because think about a scenario of if you are at 0 degrees Kelvin, that tells me that power emitted would be 0 if I plugged it in. But that can't be true because everything's emitting. So that's a hint, something's wrong, right? We need to make sure we're always using Kelvin when we're using this equation. So, speaking on that, I've got another problem here if you'd like to try this out. I want to compare the sun versus the Earth. Both of them are objects that have temperature, so both of them should be radiating. The question is, how much? I've got some values of interest here. Again, what I said before, we can go ahead and assume that E value is just 1, but you should have everything else you need to solve these things out. So I encourage you, go ahead, pause the video, work on that problem, give it a little bit of an attempt. And now you're coming back from that. Looking at this, the process for each of these parts is going to be exactly the same. No difference between the two of them. What we're going to do here is let's just kind of do these side by side, right? Since we're talking about it like that. I'm going to start with the radius of the sun. And the first thing I would like to do is I want to put this in standard units, right? Those physics units that I talk about so much. Kilometers are not standard units, but 1 kilometer is 1,000 meters. So to put that in standard units of meters, what I'm going to do is 6.957 times now 10 to the 8th meters. So assuming that the sun is a big burning ball of plasma, then its surface area is going to be 4 pi r squared, what we see down here in the bottom. When I plug that in, I am finding some sort of value. Go ahead and label that as A of sun, 5.469, 10 to the 18th square meters. We've already got the temperature is 5,800 Kelvin, so all we need to do is plug into this equation at this point. When I do that, I find a total power emitted of 3.509 10 to the 26th watts. That's a pretty insane amount. Right, again, comparing to some of our old values that we've seen, how much Earth uses. That not even close. Not even close. Right, now keep in mind, of course, Earth is not collecting all of this energy. Right, if we did, we would not exist as we would be a ball of plasma as well. Right, so we're only getting a very, very tiny fraction of a single % of this energy, but it is still a very significant amount. You might ask, how much are we collecting? Well, there's actually a fantastic way of finding out. So, I know we're going to talk about global warming down the line, but little caveat here, right? The temperature of the Earth, I'm going to just kind of paint this like this, is not changing that much. Right? The change that we are experiencing is significant. We need to talk about some of those details when we get to it. So in the grand scheme of things, I know it's a very significant value for what we're talking about life as we know it on Earth, but in the grand scheme of things, comparing rocks to rocks, the temperature change that we might be going through is not that much. So what I can say with that, if the temperature change is not that much, then the amount of heat coming in must just about equal the amount of heat going out, right? A little bit of a difference between the two, but for the most part, they should be very, very comparable values. So, part B then is telling us a little bit about how much energy is the Earth going to be absorbing from the sun. Because if this is how much energy the Earth is emitting, we have to balance that out. And the sunlight is exactly how it's the other side of that scale. So let's go ahead and tackle it like that. Similar, we need to convert this into standard meters. So 6.378, 10 to the, it would have been third, but now it's to the sixth. Standard units meters gives us a total square area of, what did I have here? I wrote this number down somewhere. 5.112, 10 to the 14th. Not nearly as big as the sun, right? A few orders of magnitude smaller. So when we actually solve out for that total power emitted, that is 1.983 times 10 to the 17th. So, right, a very tiny fraction. That is 9 orders of magnitude difference. And if you're looking at your numbers and a little bit confused, remember here, we can't use Celsius. We need to convert that into Kelvin. That temperature in Kelvin should be 287.6. If you didn't quite get this number to start out with, try that one. Probably get you to the right place. So, yeah, a very tiny amount, right? Earth is not that big in the grand scheme of things, and it's pretty far away from the sun. So the amount of light we're actually collecting, pretty tiny. You know, at least compared to the sun. But it is still a very significant amount of energy that the Earth does receive, right? Far exceeding how much energy we actually use as a species on Earth every day, every year even. So, moving right along here. Different things have what we call heat capacity. And I say things very carefully here, right? I know it's very broad language, but I'm using it very carefully here because anything that has mass has heat capacity. And what is heat capacity? I've said this twice now. Heat capacity is the amount of energy that we need to raise the temperature of that thing. That is to say, it tells us, roughly speaking, okay, so I put 1,000 joules of heat into this thing. How much did its temperature increase? Specific heat is pretty close to that. It is very closely related. Specific heat is the heat capacity per mass. So that is to say, I can look up on a table the specific heat of aluminum, but the heat capacity of a particular aluminum bar in my hand is telling me about that particular bar. The specific heat is telling me about anything made of that material. So, compares the values here, right? Speaking of aluminum, we've got aluminum, concrete, glass, some different construction materials. Their general specific heats. So, some of the things that we might notice here, some things that are quite unique, right? All of these values are in a pretty similar ballpark, right? A little bit of difference here, but not significant, not factor 10. Water is way out there. And why is it that way? Well, it's because water is really unique. So generally speaking, when we're looking at a lot of these other types of materials, right, they'll form different structures that are very solid, very rigid with each other, right? Every single individual atom might bond to other atoms in its particular area. Something else like this. And then we get these large grids of different atoms connected in different ways with each other. And that's great. You know, that's fine. That's how most materials are. And so the energy starts one of these things buzzing around just a little bit, and however much energy it takes to buzz around and how many atoms are tightly packed in that space, that's telling us about the specific heat. That's actually not a very complicated picture when it all comes down to things. Now, if you remember anything from a chemistry course you might have taken, water's a little bit unique. Even ice is quite a bit unique. Because water doesn't form structures just like this one that we're seeing above. What instead happens is that water is a polar molecule. It looks something like this. So we've got hydrogen, we've got oxygen. If you remember anything about this, that oxygen's really greedy. It pulls some extra negative charges this way, some extra electrons. So we get a little bit negative on that side. We get a little bit more positive on this side. And what that actually means is that all of these individual water molecules are kind of meeting up with each other and locking in place. The negatives aligned with the positives aligned with the negatives. And to shake the atom is a lot more difficult because it's got more glue holding it together, holding it in place. To get these things to move around, it just takes significantly more energy. And that's why water has such an incredibly high specific heat compared to some of these other things. It's just there's so much more energy that's required to actually move these molecules around. Ice has a little bit of this, but now ice has kind of formed a regular structure within itself. So even though there's still that positive to negative kind of reaction between the different molecules, now they're not just kind of freely spinning around every which way. They're a little bit more locked in place, and that means that there's just not quite as much required to get those atoms to start buzzing around. Right, now wood, where does that fall into line? Well, wood is composed partially of a bunch of carbohydrates, but it's also got a really significant water portion to it. So, and to say that wood has one specific heat is wildly inaccurate, right? There's all sorts of different spans, but this is just to kind of give you a general ballpark. You know, those are some of the values that you might expect to see, kind of a center point in this broad range that you might see. So, what do we actually use the specific heat for? Well, you can kind of look at the units to tell. Specific heat has units of joules per kilogram Kelvin. That is energy per mass temperature. Look at it like this. Q is our heat. Heat required to raise some temperature is equal to the mass of whatever I'm looking at times the specific heat of that particular material times how much I'm trying to change that temperature. So if we start from room temperature, like 20 degrees Celsius, we want to raise a pot of water all the way up to boiling. That is going to be a temperature difference of 80 degrees Celsius. That way, I can calculate, based on the mass, based on the specific heat, how much heat is it going to take to actually get up to that boiling temperature. Now, the temperature that we're looking at here, the change in temperature, this can be in Celsius or Kelvin, which is a little bit unique, but largely it's because whether we're in Celsius or Kelvin, right? If I convert this to Kelvin, then I add 273 to both sides, it gets canceled out anyways. Since Celsius and Kelvin move up at the same rate, it's just their zeros are a little bit different. It doesn't really matter which one we use. But if you want to be safe, converting to Kelvin is the first step, always a good place to be. So, a question for you, ponder on this maybe a little bit. Which objects are going to change their temperature more easily? See if you can figure this one out, right? Based on what we've just seen so far, try to be sure of your answer, right? I'm about to talk on it for just a minute here, so if you want to think a little bit longer, go ahead and pause right now. But the objects that change temperature more easily, they're the ones with the low specific heat. A low specific heat means that it doesn't take nearly as much energy to change their temperature. High specific heat means it takes a lot more energy before that temperature starts to change. So, in a problem, this is a pretty topical one. I know it's a little bit dated at this point, but it was a pretty important deal. We will actually end up talking about this one a little bit more specifically when we're in the nuclear section. You might remember, in 2011, there was an earthquake in Japan and a following tsunami. It hit the Fukushima reactors that they had. So initially, the earthquake were shutting down different pieces of the grid due to damage, but the backup generators kept the reactor online, kept everything safe. The following tsunami flooded the backup generators and meant they didn't really have the same sort of backup power. I think they still had a little bit, but really nowhere near as much to safely run the reactors. They tried to shut down the reactor immediately, but radioactive materials don't stop being radioactive just because you shut down the your actual nuclear plant. So they continued to produce a whole bunch of heat, and this was a really bad thing. There were a lot of accidents, I'm sure, very well on their mind, thinking about things like Chernobyl, thinking about things like 3 Mile Island. They wanted to avoid a catastrophe like that, so what they decided to do was pump in a bunch of seawater. That seawater coming in at 10 degrees Celsius. All in all, by the end of it, they pumped about 450,000 kilograms. So a pretty significant amount of seawater. My question here is, how much time did that actually buy them? If we're looking at how much heat can that water actually take in, how long would it take us to get to that boiling point? Go ahead and pause the video, take a little bit of time, work through this one. Now coming back, let's start our way through it. So what I'm first going to do is I'm going to look at the total energy that it would take to actually get water up to this boiling point, right? I think that's the key part first. I'm going to ignore this 25 megawatts, not milliwatts, big difference. For just a little bit, I'm going to focus on the water. So what we know here is that we are going a temperature change of our end point is 100 Celsius. Our starting point is 10 Celsius. We've got a total change of plus 90 degrees Celsius. We've got the mass of 450,000 kilograms. And if we look back at our table from here, the specific heat of water is 4,184. And seawater is a little bit different, but not different enough for us to worry about it. So with all of that in mind, go ahead and write this out. 4,184 joules per kilogram Kelvin, or Celsius, totally fine. So the total heat that water is able to take, plugging in all these numbers that we've got right here, I've got a value of something like 1.695 times 10 to the 11th joules, which again, a lot of energy. But time is going to be that total energy divided by the rate of putting energy into that water, the power currently being output by each reactor. And that's not power as in electricity, that is power as in heat. Unwanted heat at that. Solve those out and I get a number something like 6,778 seconds, right? And we can confirm, yes, right around 6,780 seconds. Doing a little bit of rounding. If we convert that into hours, so it's a little bit more meaningful, that is about 1.88 hours. Not a lot of time. Not a lot of time at all. So, pause for a minute, put a pin in this problem. I'm going to talk about this just a little bit more. I've actually got a second part to it. First, I want to talk about something else. Not only can we change the temperature by adding heat, but we can also change the phase. So the three big phases that we typically worry about, solid, liquid, and gas, it actually takes some energy to transform between those two, right? It's not free. It doesn't just happen automatically. You have to either add or take away energy. So when we're thinking about something that is ice cold, what's actually happening there, you pour in the ice melts until everything is at the freezing point of water. Any additional energy coming in doesn't actually heat anything. What it does is melt the ice. So it stays at that ice cold temperature until all of the ice is gone, and then it can start rising in temperature again. Right? Now, of course, fluids don't always behave as ideal as we would like them to be. There's a little bit of difference here, but for the most part, that's how a lot of these things try to behave. And that energy that it takes is something that we call heat of transformation. And we've got some fancy names for these, but if you want to just focus on it as solid to liquid and liquid to gas, totally fine by me. So, looking at them, we've got a variety of different melting and boiling temperatures. So here's our melting temperatures, our boiling temperatures. The LF, this is our solid to liquid. The LV, this is our liquid to gas. So and again, we've got a lot of commonality here. Everything about a 10 to the 5th. Some of them not quite earning it, but getting pretty close. Everything's around the same order of magnitude until you start to look at what is going on with water. Right? Again, higher than the rest of them. Because, again, the exact same problem as before. Think about what's going on with a gas. Those molecules are no longer nearby neighbors. They're now quite distant. They're flying off in all sorts of directions. So all of these neighbors that have attached themselves together, positive to negative, negative to positive, these things that have formed this large ensemble, all of them grouping together, are suddenly being asked to separate. And that's difficult. It takes a lot more energy than other materials because not only do you have to get them excited enough to fly off, but you've got to get them excited enough to fly off and excited enough to leave their neighbors. It takes a little bit more energy than everything else because of that. So, the reason I wanted to do this before I talked about the last problem is because when they pumped in that seawater, right, they knew a little bit of science. They knew what was going to happen. getting the water to the boiling point was not the only thing they were trying to do. What they were relying on is that we have to get the water up to that boiling point, and then we also have to boil the water away. The big issue with a nuclear reactor shutdown like this, when we're in danger of a nuclear meltdown, is typically because that heat has nowhere to go. Even if that heat is going into generating steam, that's totally fine. It still has somewhere to go. So the question is, if we boiled all of that seawater off, how much more time did we just buy ourselves? Pause the video, give it a shot. Now coming back into this one, we're going to have the exact same mass of water. So let's take our brand new equation. Q is equal to the mass of the water times that heat of vaporization, or liquid to gas. Liquid to gas is our 22.6 times 10 to the 5th joules per kilogram. We've got a mass, 450,000 kilograms. When I plug all of that in, I get this thing is going to suck up 1.017 10 to the 12th joules. So again, compare some of these numbers. We're getting about 10 times more energy packed into boiling this water. Now, do the exact same process as before. Same heat being put out. Divide that heat by the rate of heat that the reactor was outputting, and what we get are now 40,680 seconds, or convert that, 11.3 hours. So 2 hours, maybe not that much, but now 13 hours in total, that's something we might be able to work with, right? Confirm it here, about 40,000 seconds. So, and they did catch a bit of flack for this, right? Again, I'll talk about this a little bit more when we get into this section, but they did catch a fair amount of flack for this because putting that seawater in there, and then realistically, they didn't just pump it in and then leave it there and then pump more in. What they did is they pumped a little bit in, they spit some back out, they pumped some more in. The problem with doing something like that is that, it is still radioactive material that it's absorbing heat from. That radioactive material does interact with the seawater, right? It's not a ton that it does, but it does create a little bit more radioactive seawater than normal. It actually forms, if you remember we were talking about that deuterium, it forms deuterium, or we call it heavy water. And it is naturally found in the ocean, but the amount that was being put back into the ocean was much higher content than is naturally found. So it was not a good situation either way. I can't necessarily put myself in those shoes. That's, way above my pay grade to be able to make decisions like that. By the time they were in that situation, there was no good solution. But we'll talk about that a little bit more next time. We'll talk about some of the details leading up to that, what exactly was the problem, what they're doing about it now, all in good time. For now, let's go ahead and keep up with this cheery topic that we're considering here, right? Considering something like energy quality. I think this is going to be the last thing that I'm going to talk about here. We've got a few other details, but I'm going to talk about these next time, so I think we'll just call it there for now. Energy quality is talking about all of the different features that we might look for in some source of energy, right? Generally speaking, when we're looking at these things, mechanical energy is usually king. It is one of the best things that we can have, largely because it is very easy to transfer to other places, right? The conversion rate is fantastic. It's delightful, right? Compared to something like a lithium-ion battery where you get a 70% conversion rate. If you're talking gravitational potential energy to kinetic energy, you're getting like 99% efficiency. It's fantastic. But unfortunately, when we pull fossil fuels up out of the ground, they don't just start running or pulling things up, lifting blocks or anything else like that, right? We burn them. That's heat. That is thermal energy. And thermal energy is not mechanical energy, but we can use engines to transform it. So let's do a quick comparison here. There are 3 different representations of 200 kilojoules of energy. A 2-ton car moving 30 miles per hour, a teaspoon of gasoline, or a gallon of water heated by 10 degrees Celsius. The question is, how easily can we transform from one of these types of energy into other types of energy? And how many other types of energy? And you can think about this for a little bit, but I'm going to say that this is probably already ordered up how I think they should be ordered. A gallon of water heated by 10 degrees Celsius, well, that happens in a warm room. How do I actually extract that in any meaningful way? It's very difficult. I guess what I could do is I could use it as a temporary heating pad or something, but even then, it's not going to be all good. It's going to be wasting a lot of that heat that I'm looking at, and at a certain point, it's going to be cold enough that it doesn't really matter. So, not a very good source of energy, not very high energy quality. A teaspoon of gasoline, now that's really easy to transport, right? Exceptionally easy to transport. Anybody can do that. But the next best place it can go is into thermal energy, which now we have to deal with an engine and other features like that. So a little bit better than the gallon of water, but not fantastic. Finally, a 2-ton car moving 30 miles per hour. Well, we like a lot of that, right? Admittedly, what do you do with that energy now? Well, it's difficult for you guys to see, but there are a lot of industrial things like large industrial flywheels that can be used. There's actually a new startup company that's working on storing energy as stacked bricks for that gravitational potential energy. And then when they need the energy, they simply lower the bricks on a crane and they convert that into electric. It's a kind of cool project. I'm really intrigued to see where they go with it. But I bring this up to say the 2-ton car, well, that's something that we do every day. That's very useful for us. The gasoline itself is not particularly useful without the car. So I'm going to say the 2-ton car, that is probably the best case for that energy. A lot of the games that we need to work with here is we need to look at, for that energy, how easy is it to obtain? How easy is it to transport? How easy is it to turn it into something else that we actually want? How much effort does that take? Is that conversion process easy? Is it very wasteful? Are we able to do this without any sort of side effects? There's a lot of things that we really need to worry about here. And the answer is there's no good solution. There's 1,000 all right solutions, but that's just reality. That's what we got to contend with. So I think that's where I'm going to call it for now. We're going to talk about some of these thermodynamic things in the next chapter. So we will come back. We'll see a lot of these slides again. If you'd like to take a look ahead of them, right? No harm in doing so, but we will talk about this stuff again quite soon. But until then, that has been the week 3 set of lectures. I will see you next time for week 4 with thermodynamics and fossil fuels. Have a good one.